Okay, thank you so much, Adrian, and thank you for the invitation. So first, I will give a motivation, then I will give some results in the sense of which seatband model, and finally, I will present some results in the spirit of the stroke seatband model. So first, I will present the Wright-Fisher model. We need to consider a haploid population with a fixed number n of individuals in each generation. So for example, here, if we are in generation number 1, every individual have to choose their parent in the previous generation. So that means each individual from generation k plus 1 chooses independently and uniformly at random its parent from generation k. So for example, here, if we go back in the time and if we take a sample of size 6 and we go back in the time until find the common ancestor of all these individuals in the sample. So then what the dormancy means? We call a dormancy or seatband effect if individuals can deactivate for some time and then awake. So for example, here in the first picture, we have a desert where there is empty about the flowers. We can see any flowers, but some time after or some years after, suddenly appear purple flowers. So that means that individuals deactivate for some time and then they awake. So we have the Wright-Fisher model with dormancy. So it's similar to the Wright-Fisher because we have a haploid population with a fixed number, but the difference is that each individual chooses its parent from a random generation in the past, not necessarily in the previous generation. So for example, this individual, it doesn't have offspring in the generation number 1, but in generation number 2, this individual has an offspring. The time that individual can be in the dormancy state is of order number 1. So for example, here this individual finds its parent 3 generations before. And these two individuals, this individual can find its parent 1 generation before. Also, there are another kind of Wright-Fisher model with dormancy, but we call this a strong dormancy because in this model, there are 2 kinds of population. One population is the active individuals, or also we call plants. And also we have inactive individuals that also we call seeds. And in every generation, we have the same size of the population. That means if we have here 5 plants in generation number 1, we need again 5 plants. And if generation 0, we have 3 seeds, we need again in generation number 1, 3 seeds. And we have a change of a small proportion between active and inactive individuals. That means if 1 plant becomes 2 seeds, we need 1 seed becomes 2 plants. Each active individual chooses its parent in the previous generation. Only active individuals can reproduce. If we have inactive individuals, they can reproduce. The difference between a strong model and weak model is that the time that one individual can be in the dormancy state is of order n, is order capital N. And here we can see the active individuals are inactive individuals. That means we have like 2 populations. So if we have a Roy-Fisher and we're scaling the time by n when n tends to infinity, in the backward time we have a Kingman coalescent. In the case that we have a weak seatband, we have a Kingman coalescent slowed by a constant. And in the case of a strong seatband, we have the seatband coalescent. So the objectives is that we extend the Gach-Kron-Lascour results. That is, we consider a Cannings model instead of a Roy-Fisher model, and we extend the results on the limit genealogy process. Also, we present a duality result between forward and backward process, and we obtain limit result for the forward frequency process. So I will present the Cannings model with dormancy. So also we consider a haploid population of constant size at each generation, but in this case, the vertex set represents the whole population. So in this case, every individual in the population is represented by a vector where the first coordinate corresponds to the generation and the second coordinate corresponds to the label from 1 to n, where n is the total size of the population. Also, we have a probability measure, and W gives the reproductive weight of the individuals B in the population. Also, we have a collection of independent mu distributed random variables, where this random variable says how many generations ago individuals, the father of individual B is living. And each generation is independent. So for example, in the case of Gach-Kron-Lascour, in this case, mu n has a finite support. That means mn is equal to m, and this probability measure is equal to this in this case. And so first, I will present how we construct the forward frequency process. So the gray circles represent one type in the population, and the white circles represent another type in the population. In this case, n is equal to 8, and mn is equal to 3. Mn says how many generations ago we can find an ancestor. So in this case, I will construct this vector where the first coordinate corresponds to the generation 0, and I see how many gray circles I have. I have 5, and the total size of the population is 8. So in the first coordinate, I write 5 over 8. The second coordinate corresponds to the how many gray circles I have in the generation -1. So in this case, I have 4, and I write 4 over 8. Then I move one generation. So now I see how many gray circles I have in generation number 1. So in this case, I have 5. So that's the reason that I write 5 over 8 in the first coordinate. The second coordinate corresponds to the generation 0, and the third coordinate corresponds to generation -1. So all the individuals, the offspring, have the same type that their parent. And B1, B2 until B8 are the samples that I take and the initial. So this is the sample or the individuals that I take in the beginning. So then we have an ancestral process, and we construct this also like a vector. But in this example, mn is equal to 2. So in this case, we only see 2 generations. The blue circles represent the members of my sample, that is this. And I see generation 0. How many individuals or ancestors I have in generation 0? So in this case, I have 4. So this corresponds to the first coordinate, and the second coordinate corresponds to the ancestor that live in generation -1. So then the second, I move 1 generation and I see how many ancestors I have in generation -1. So I have 1 and 2, because this corresponds to the ancestor or the parent of this individual, B2. So I write 2 in the first coordinate, and then I see how many ancestors I have in generation -2, and I have also 2. This corresponds to the ancestor of the individual B1, and this corresponds to the ancestor of individuals B4 and B3. So that's the reason that I have 2 in first coordinate and 2 in the second coordinate. If you have a question, you can interrupt me. Then our first result is that the forward frequency process and the ancestral process are sampling duals. So we have this equality in the expectation where H is the probability that the set, but this corresponds to the set composed by the most recent ancestor of the individuals of the sample. But observe that this sample corresponds to the forward frequency process, and this corresponds to the ancestor. So in this case, we have a sampling duals that corresponds to this probability. But we want to obtain a moment duals, so we construct a little different process, that also corresponds to the ancestral, but this process we call windows. And the difference is that in this case, the first is similar to the ancestral process, but the P1 that corresponds to the how many ancestors I have in generation -1. So in this case, I have 2 ancestors, so I write 2. And then I need to know how many ancestors I have in generation -2, but the difference is that in this case, I don't see only the ancestor. I see how many arrows touch the red circle. So for example, I have 1 arrow and I have here 2 arrows. So in total, I have 3 arrows that touch the ancestor. So in this case, I write 3 in the second coordinate. Then I move 1 generation and I see how many ancestors I have in generation -2. And again, I count how many arrows touch the ancestor in this generation. So in this case, I have 5. And all the ancestors of my sample live in generation -2. So that's the reason that I write 5 in the first coordinate and I write 0 in the second coordinate, because all the ancestors live in this generation. So this is a little modification with the ancestral process, but we obtain that this window process and the forward frequency process are moment duals. So that is the reason that we construct this a little different process. So in this case, we have this result. Then Moll and Sagitov have this theorem that say that in the Canning model, if Cn is the probability that 2 individuals have the same parent 1 generation before, and Dn is the probability that 3 individuals have the same parent 1 generation before, if Cn converges to 0 and Dn over Cn converges to 0, we have a Kingman coalescent in the limit. And if Cn converges to 0 and Dn over Cn converges to something that is different to 0, the He coalescence appears. So in our case, we have a similar result. In this case, beta n is equal to the expectation of J. If you remember, J says how many generations is the father of B is living. So if Cn over beta n squared converge to zero, and Dn over beta n by Cn converge to 0, we have that the Windows process converge to a block counting process of a Kingman coalescent. These only are technical assumptions. And in the other case, if beta n converge to beta, and we assume that the ancestral process of a Canning model is driven by this probability measure, and we denote by Cn, such that Cn converge to a block counting process of He coalescent. In the case of the Windows process, converge to a block counting process of He beta coalescent. So also observe that in this case, the Windows process is rescaled by this constant, and in this case, Windows process converge to a block counting process of a He beta coalescence. So that means that He beta coalescent is that, for example, if we take the infinite simplex in the interval 0, 1, for example, here we have this partition and beta is bigger than 0. We need to divide every element by beta. So that means that in this case, the slow down the coalescence by this component beta. And finally, we have this result that says that in the Kingman case, the forward frequency process converges to a vector where every coordinate of this vector is a Fischer diffusion. While in the case of the He, we have that the frequency forward process converge to this vector, and this vector have m identical coordinates, and every coordinate is a moment dual with the block counting process corresponding to the He beta coalescent. So all of these are results in the sense of the weak seatband model. And now I will present some results in the sense of a strong seatband model. Do you have some questions until now?
Yes. Hi, Liz. I hope you're doing well.
Hi, Ali.
So I was wondering, did you try to also study the convergence for the genealogies, or only focused on the block counting process?
Sorry, I didn't listen to the first part.
Did you study the convergence of the genealogies as well, or maybe
in the weak seatband?
Can you repeat that? Sorry. Yes, I was just wondering if you only studied the weak convergence of the block counting process.
Yes, we only study the convergence in the sense of the weak model. That is with this construction, with the Windows process and the ancestral process. So in this case, we have convergence, and also we have a moment dual results, that this is the important results in this construction. But then I will present in the stroke seatband a little different results. I will talk about the coalescence.
No, sorry. Can you hear me better now?
Yes.
Okay. So I was wondering, so you mentioned this result for the convergence of the block counting process, right?
Right.
did you try to address the convergence of the genealogies as well?
Yes, I understand. Now, in this case, we only present the block content in the convergence in the block content coalescence.
Okay. Well, okay.
Similar. Yeah.
But at least I guess you have at least the correct time scale that you would need if you wanted to study the genealogy. Okay.
Yes.
Okay.
Yes. Yeah.
Great. Thank you.
Yeah, you're welcome. Okay. So now I will present some results in the strong seatband. So we try to answer the question, the different genealogies affect the number of observable mutations? So first we need to remember some results in the Kingman coalescent. So let Ln be the total length in the Kingman coalescent that is equal to this sum where Ej is a random variables are independent and exponentially distributed with this parameter. And the main result in this case is that Ln over log n converge in probability to 2. So this is the result in the Kingman coalescent case. But we can add mutations to the Kingman coalescent by simply superposing a Poisson process in the ancestral lineages. Sn will be the number of mutation, and conditional on Ln, the number of mutation that we see in the sample has a Poisson distribution with this parameter, where mu is the mutation rate. So if we know the asymptotic behavior of Ln, we can deduce the asymptotic behavior of Sn. So that is the importance of to know the total length of the tree. And so now this is the seatband coalescent. The block counting process of the seatband coalescent is the two-dimensional Markov chain with this rate. So we have 3 events in this case. The first event is that we can have a coalescence with this rate, or we can have the activation. This means that one plant becomes seed, or we have a reactivation. That means that one seed becomes 2 plant with this rate. So for example, here, the crosses represent that one plant becomes 2 seed or 1 seed becomes 2 plant. And if we see this time, we see that we have coalescent. So we have now this block. In this case, this plant becomes 2 seed. In this case, we have a coalescence, and then this becomes 2 seed, and this is the same. It doesn't change. So now we want to answer the question, what is the length of the seatband coalescent? So we consider the seatband coalescent starting with n plants and no seeds, in this case. And we construct this stop time. We say that theta n is the first time that a seed becomes a plant. So before to this time, we only have 2 events, coalescence or the activation. And we called this part of the tree Kingman with frozen phase. After this time, we have the 3 events. We have coalescence, reactivation, and deactivation. And sigma n is the first time that we have only one individual, or is the most common recent ancestor. Is the time. So we have this result. The seedband coalescent starting with n plants and no seeds. The total length over log n converge in probability to 2 plus 2 C1 over C2. Ln is equal to the active length plus inactive length. So active length corresponds to the plants or the active individuals, and this inactive corresponds to the number of seeds over the time 0 to the most recent common ancestor. So if we consider the seedband coalescent starting with n plants and no seeds, Sn is the number of mutation in the seedband tree, and mu is the mutation rate of the active individuals, and kappa corresponds to the mutation rate for the inactive individuals. So we have that the number of mutation over log n conversion probability to this 2 times mu n plus 2 times kappa C1 over C2. If you remember, C1 is the rate with the one plant becomes seed, and C2 is the rate where one seed becomes plant. So we have a picture of the tree. So we find that the active length over log n conversion probability to 2. So if you remember, this result is very similar in the case of the Kingman coalescent. And in the inactive length over log n, conversion probability to 2 times C1 over C2. And also we find an approximation of the number of seeds in this time. You remember theta n is the first time that a seed becomes to plant. And also we find an approximation of the number of seeds in this time. So the intuition behind this result is that as we started with n plants and 0 seeds, we need to accumulate enough seeds. And if you remember, C1 is the rate with the one plant becomes 2 seeds. And then we need to empty the seed bank, or we need that all seeds becomes plants. So, and if you remember, C2 is the rate where one seed becomes to plant. So that is the idea of this result. And this is that before to theta n, we only have 2 events, that is coalescence and deactivation. So many coalescence occurs before to theta n. Okay. So if we consider a seedband coalescent starting with n plants and no seeds, we have that the number of plants at time theta n over log n converge in distribution to zeta, where zeta is a appreciated random variable with these parameters. And the number of seeds and this time theta n over log n conversion probability to 2 times C1. And finally, log n times by theta n conversion distribution to t, where t is an exponential random variable with these parameters. Okay. One idea of the proof of this proposition is that one coupling which provides the reactivation, that means that we use this model in particular to prove that the number of seeds that survive up to moment theta n is of order 2 times C1 times log n. So that means that we only, in this model, we only have coalescence and deactivations. And we use a second coupling where we start with 2 times C1 log n seeds. That means in this case, we don't start with 0 seeds, we start with this number. And we obtain a lower bound for theta n and an upper bound for the number of plants in this time. So that was the idea. Finally, we have a sample formula that is like a style of the Ewens simple formula. So in this case, we have like a Chinese restaurant process, if you have listening about that. But in this case, we start with, for example, here in time theta n, we have 2 plants. So it's like we start with 2 tables with 1 individual in each table, and we go back in the time. So if one customer sits in the same table, it means that we have a coalescence. But if one customer opens a new table, it means that one plant becomes to seed. So at the end, I have that in the old tables, I have the number of individuals that they never visited the seed bank, and the new tables have the number of individuals that visited the seed bank in one moment. Okay, so we have this theorem that says that the probability of all tables and the probability that new tables, how many individuals there are in each table, but is conditioned with the number of plants that we have at time theta n. So we have this result. And also we have an approximation about the probability that this is not conditioned with the number of plants that we have at time theta n. So we can find an approximation in this case, where the variable OI and RI can be inferred if we are capable of deciding if a present individual has visited the seed bank or not. This is all our results that we have in these two projects. So this is all. Thank you.